When an artificial intelligence makes a mistake, no human steps in to manually rewrite its code. Instead, a hidden algorithmic engine operates in the background, allowing the system to calculate its own failure and autonomously fix its internal wiring. This diagram maps out a standard neural network architecture. During forward propagation, data flows strictly from left to right. It starts at the input layer, gets transformed by tunable weights and biases inside the hidden layer, and finally arrives at the output layer. But let's assume this network is completely untrained. We feed it an image of a 2, the data cascades forward, and the final prediction is completely wrong. A red node lights up, indicating the network guessed an 8. Here is where we measure that failure. We calculate the exact mathematical difference between the incorrect output the network gave and the correct output we wanted it to give. This specific measurement is known as the loss function. The primary objective in machine learning is to find the most efficient mathematical path to minimize this exact error, driving it as close to 0 as possible. Methodical. Without a mechanism to calculate and react to this loss, a neural network is just a static math equation. Recognizing the precise size of the error is the mandatory first step before learning can actually occur. This is where an algorithm called backpropagation steps in to distribute the error backwards. Looking at our 10 output nodes, the network calculates that our target node, the number 2, must go up, while the other 9 incorrect nodes must be driven down. The required adjustments for each node are strictly proportional to how far away they are from their correct target value. A wildly incorrect node receives a large nudge, while a node that is already close to where it should be requires only a tiny adjustment. If we isolate just that target output neuron, we run into a core mechanical problem. How do we mathematically force this specific neuron's activation value to increase? We have 3 distinct mathematical levers at our disposal. First, we can modify the neuron's personal bias. Second, we can adjust the weights of the incoming connections feeding into it. The third lever involves changing the actual activation values of neurons in the preceding hidden layer. But consider this. If we are going to adjust those incoming weights, which specific connections will yield the greatest mathematical impact on the final output? The highest leverage is found in the brightest, most active preceding neurons. Because their weights act as multipliers on a larger base number, strengthening these specific connections exerts the strongest influence on the final result. This process follows a highly targeted optimization, where the network exploits its most active connections to achieve the maximum possible reduction in error. But there is a systemic conflict in this process. While our target neuron demands specific changes to the preceding layer to boost its own signal, the other output neurons demand completely opposite changes to lower theirs. To resolve this, the algorithm adds together all these competing desires. It calculates a single, unified master list of proportional nudges for the preceding hidden layer that balances the mathematical needs of every output neuron. Once that hidden layer's master list of nudges is set, the exact same calculation repeats backward to the next layer. This recursive mathematical process ripples deeper and deeper into the network. Calculating these precise ripples for tens of thousands of training examples before taking a single step creates a significant computational burden. Looking at this topographic map of a network's cost surface, we can see the primary workaround: stochastic gradient descent. Instead of processing the entire dataset at once, the training data is shuffled into small subsets called mini-batches to calculate faster approximate steps downhill. Trading mathematical perfection for this approximate path yields a substantial gain in training speed. This error rippling process functions exactly the same whether data moves linearly in static image recognition or through the complex loops of a recurrent neural network analyzing time series data. This system relies on millions of proportional, aggregated adjustments rippling backward to systematically eradicate error over time.